In 1932, Frederick Bartlett published the book Remembering, which discussed 20 years of experimental work on human memory and culture. And in his book, Bartlett introduces the method of serial reproduction, which you're probably actually familiar with through the children's game of telephone, where information is passed down a chain, transforming along the way. So Bartlett asked a participant to come into his lab and to read a Native American folktale. He was British, and so was his participant. In particular, it was a story called War of the Ghosts, and it was about a page or two long. Then what he did is he took the story away, gave the participant a pen and a piece of paper, and said, recreate the story from memory by writing it down verbatim. He then used the story that one participant retold as the stimulus for the next participant who came into the lab, just like in the game of telephone. And what he found is that as the stories were passed down the chain, they transformed. They shortened, they lost detail, and they became more similar to stories from the listener's own culture. This technique is more generally called a transmission chain, and at each step of the chain, the transmitted information is transformed. And so long as a few technical conditions hold, repeated application of a transformation like forgetting leads to erasure of the information that's contained in the input, leaving behind just a signature of the transformation process itself. Modern reincarnations of the transmission chain technique, they usually consider stimuli that are a little easier to analyze than just free-form prose. So Michael Kalish and colleagues, for example, studied function learning, examining what happens to the functional form of a relationship as it's passed from person to person. And one example of learning a function is, you get a rental car and you have to determine how much the car accelerates when you push down on the gas pedal. So on each trial of the Kalish et al. Experiment, the observer sees a blue bar like this one, horizontal bar, and is asked to guess the height of a red vertical bar, the maximum possible size of which is shown by the outline. The observer is told that there is some relationship between the sizes of the bars, but critically, they aren't told what exactly that relationship is, and it's their job to learn it. So go ahead, how big is the red bar? Say something out loud. I can't see your fingers.
1/5 of the height.
Okay. Yeah. So I heard a few things. Somebody guessed a fifth. I think that's reasonable. I think that typically what most people guess is that it'll be about the same size. So let's say that we guessed that it was the same size, and that's a reasonable guess, but it would be wrong. In fact, the red bar ought to have been that size. Okay. So now let's move on to the next trial. Here's another blue bar. How big do you think the red bar is now? Okay, great, so much bigger. And feedback, yep, that's exactly right. So the learning process continues on in this way. And you may already have a sense of what the relationship is between the bars, but you should be at least a little bit uncertain. There are many hypotheses that are consistent with the limited data that you've seen. This problem of function learning has been well studied in the cognitive psychology literature, and it turns out that some functions are much easier to learn than others. The easiest is the positive linear function x equals y. Slightly harder is the negative linear function x equals negative y. Harder still are sinusoidal and other curvilinear functions, and random mappings of x and y values are very hard to learn. In Kalish et al.'s experiment, they first train a participant on a particular function and then test them by showing them the blue bar and asking them to produce the red one over and over, but without feedback this time. And critically, the test trials that are used for that first participant are actually used to train the next participant in the chain, just like in the game of telephone. And so in this way, it's possible to examine the effects of transmission on the functional form of the relationship as it's passed from person to person. So let's take a look at the data. What I'm going to show you is 4 chains, A, B, C, and D. Chain A is seeded with a positive linear function, B with a negative linear one, C with a kind of sinusoidal curve, and D with that impossibly hard random mapping of x to y values. And so let's see what happens as the information is passed down a chain. Here's the first participant who learns directly from the original ground truth function. Here's the second who learns from the first. Here's the third who learns from the second. The fourth who learns from the third. The fifth, the sixth, the seventh, the eighth, and the ninth. And so what's clear is that no matter the original function, the chain reverts to those functional forms that are easiest to learn. And in this way, the transmission chain reveals the participants' inductive bias, their assumptions about what kinds of relationships are most probable. This kind of system can be formally modeled as a Markov chain, defined by a transition matrix that specifies the probability of going from any one given state to any other state. So going back to the game of telephone, for example, the transition matrix defines the probability that a given sentence will transform into another one. So that, for example, laid him on the green becomes lady on the green. You can prove that if the individual learners are Bayesian, the long-term dynamics of a transmission chain converge to a stationary distribution that's the prior assumed by the learners. And so what that means is that in the long run, the initial function that's passed into the chain is irrelevant. All that matters for the long-term dynamics is the bias of the individual learner. And the transmission chain reveals these biases. Experiments where participants are arranged into some kind of network, like a linear chain or a fully connected network or a scale-free network, are very common, and particularly when people are asked to transmit information between them. So for example, in studies of human cooperation, it's pretty common to arrange players in some sort of a network and ask them to play individually, pairwise, play a two-player game like a prisoner's dilemma. That's where you take two people, they either get to decide to screw each other over and get a little bit more, or to cooperate and get a little bit less, but the worst case scenario is that they both screw each other over and then they get the worst possible outcome. And so people study all sorts of factors, how it affects the outcome of and evolution of a population on a network like this, in terms of what happens with reputation, what happens in terms of network structure, what happens over time. That's not the only field where people study experiments of this kind of people arranged in networks. People do this in economic decision-making, organizational behavior, social learning, language learning, human-in-the-loop computation, interactive genetic algorithms, evolutionary dynamics, social contagion, and more. And one of the things that's common to all these experimental paradigms is that the logistics of running the experiments are complicated. They often require coordinating many people over a long time scale and finding enough physical space to actually isolate participants and control the way they interact. And so for this reason, studies are often limited to simple population structures, small sample sizes, and only very indirect interactions between participants. Really, running these kinds of studies in brick-and-mortar labs is hard. So one way to overcome these challenges is to use online crowdsourcing to recruit and manage participants. In particular, behavioral and social scientists have begun to move from brick-and-mortar laboratories to the web, where participants are recruited through crowdsourcing services and use browsers to interact with web applications hosted on a server. But then this presents a new challenge, which is actually building the software. And there doesn't exist a general purpose tool for efficient experimentation of this kind that has a scope that would allow you to run experiments of from all these different fields. Our lab alone had 6 different systems that people used internally for running studies like this. And what that does is it makes it hard to share code, hard to replicate other people's experiments, and hard to build off the work of others. So our solution was to build Dallinger, a Python-based platform for running crowdsourced behavioral and social science experiments. Just as an aside, Dallinger is named after William Dallinger, who was actually a British minister and scientist who carried out one of the first experiments on evolution using this incubator. So in the experiment, what Dallinger did was he took a culture of microbes that thrive at room temperature, but which would be killed by high heat. And over the course of several months, what he did was he slowly increased the temperature in the incubator. And what happens is that the microbial culture evolved to actually survive at the higher temperatures, and eventually losing its ability to survive at room temperature. And this was a strong demonstration, and a very early demonstration of evolution by, in this case, artificial selection. So Dallinger, our crowdsourcing system, handles the full pipeline of experimentation, from recruiting participants from online crowdsourcing services, bringing them into our online lab, arranging them into a sort of network structure of your choosing, determining the ways that they interact, running them through some kind of structured or unstructured interaction, and then managing the resulting data, of course getting their informed consent before the experiment, and then managing the resultant data and paying them and all that. Beyond running experiments entirely with people, we also aim to create a tool that enables free mixing of human and non-human players, in particular bots or program-defined strategies, and also hybrid agents that make use of both human strategies and machine decisions. So I'll just give you a little sample of, like, suppose a colleague sent you a link to a repository that she said had like a code to run an experiment, and she wanted you to replicate it. So how would you do that? So step one, install Dallinger. What that'll give you is a Python library called Dallinger and a command line utility called Dallinger. Basically, everything's going to be called Dallinger here. First, you're going to set it up. You're going to give it your AWS credentials and all that, and then you're ready to go. You write Dallinger deploy, and that's going to kick off a chain of events that will result in you getting data that is a direct replication of the experiment code that you were sent. The first thing that's going to happen is your experiment will be assigned a universally unique identifier. It's going to get automatically pre-registered, a very lightweight version of pre-registration on the Center for Open Science. The code is going to be backed up as a snapshot of it, timestamped in an S3 bucket. And then a web server will be spawned. This makes use of Amazon Web Services and Heroku. There's a web application that communicates with a component that is a recruiter. That recruiter connects to crowdsourcing services, for example, Amazon Mechanical Turk, though we have a few others, including some collaborations that we have with companies that actually are building new kinds of crowdsourcing recruitment for behavioral and social science experiments. You could also recruit bots. That'll recruit your participants. Here's person 1, 2, and 3, and bot number 1. They interact with each other via communication with this web application. Eventually, your experiment's done, and it backs up the data, and hooray, you've replicated the experiment. The technology stack that underlies all this, most of it's written in Python. We make use of Redis for communication with the server in real time, and WebSockets. It's built on Heroku and Amazon Web Services, and there's several recruitment services, including Mechanical Turk, IST Research's Pulse Recruiter, some email-based recruitment, and the backend technology for storing the data is a Postgres database. We connect to it via SQL Alchemy, just naming everything that's useful in this. It's a G-Unicorn server. We use PyTest for testing, and then we're the only one of these that I did not have time to look up how to say it, but I'll go with the most impossible pronunciation, which is Gevent, G-E-V-E-N-T, G-Event. Somebody here must know. What's the canonical pronunciation? G-Event? Okay, fine. Not Gevent? Okay. So today I'd like to take you on a brief tour of some of Dallinger's major functionality, in particular by doing that through a discussion of the technical challenges and opportunities that we came across when developing it. And in particular, I'd like to focus on interoperability, scalability, reproducibility, and sustainability, which are 4 topics that are continually on our mind and have been when developing this. So let's start with something that's a kind of mix between interoperability and scalability. The most common factors that vary across the experiments of the kind that we consider in our conceptual universe is 1, the network structure that participants are arranged into, 2, the process that takes place over that network in the sense of who communicates with whom and who connects to whom, and 3rd, the task that the individual is going to complete. And in Dallinger, the network structure is determined by a network construction algorithm of your choosing. And in particular, that's going to define both who connects to whom and what happens when a newcomer joins. So this is the case of a transmission chain where we have this create network function, and you get to decide what is the network structure that you want. Here, for a transmission chain, the network structure is a chain. But then you also need to specify the process that happens over that network, which is when you add somebody to the chain, what happens? And in a Bartlett-style transmission chain, it's pretty simple. When you add the person when you add somebody to the network, you have to actually add them to the network, and then if they have any parents, that is, if they have anybody who was there before them, find the one who was there most recently, and then send a message from the parent to the newcomer, and then make sure the newcomer gets the message. And that defines the whole process of a transmission chain. What's nice, though, is that the user has 3 options for specifying a network structure and a process. So first, they can use built-in networks like the one that I have here, a chain. We have lots of other networks like a scale-free network, a fully connected network, and a few others. But second, they could also specify their own network construction algorithms, like you can in this or a process over the network, like we're doing in the add node to network. And third, they can import external Python modules for network construction algorithms, such as network X. And once the user specifies the network structure and process, Dallinger will handle the rest, recruiting people in exactly the way specified by the network structure. And this becomes particularly useful when you're running experiments with complex network structures. So for example, the most complex experiment that we've run on Dallinger makes use of what we call a discrete generational network. So in the experiment, we were trying to understand the evolution of social learning, which is our ability to learn from others as opposed to learning directly by interacting with the environment. So the most common way to study the evolution of social learning is to do it using agent-based simulations, where you set up a simulation and you can actually track by making lots of assumptions about the structure of the mind, the structure of social learning, the structure of genetic transmission, the structure of cultural transmission, what the dynamics will be. However, what we wanted to do was to study the precise interaction between human cognitive factors and the evolutionary trajectory, just like in that Bartlett transmission case. And so what we needed to do was to run an evolutionary simulation, but with people. And so in the experiment, we actually recruit a batch of 60 people to serve as the first generation of the experiment. These people all learn directly from the world. We then Dallinger sends them away, brings in a new batch of 60 participants, each of whom is linked up with somebody from the previous generation. They inherit artificial genetic information that controls what kind of learner they are. Are they the kind of person that learns from the world or who learns from observing others? And then they actually inherit cultural information, which is if they're a social learner, they get to actually observe what somebody else did what somebody else decided when they did the task. Send that batch of 60 away, bring in another batch, and we actually run this for 40 generations, meaning that we have a network that has 2,400 participants arranged in just the right way. And this is, in fact, we actually ended up recruiting about 3,200 people so that we can get a yield of 2,400. And this is the point of bringing this up, is that this is on the other side of the threshold of what is even conceivable to do in the lab. And end to end, that experiment took about a week with little intervention on our part. And so it's really just a step function change in scale that we have available to us. This is a lot of code. I don't want you to read it all, but what I just want to show you is that this is the add node to network function for this kind of evolutionary process. And what you see is that the kinds of entities that we're talking about here are exactly like it was in the Bartlett transmission case. Parents, children in a network, who's connected to whom, conditional statements like if a certain property of a certain agent is this way or that way, then either have information be passed from this person or instead be passed from the environment. Okay. A second challenge and opportunity that's related to interoperability was figuring out the right kind of format to use to store the data. What we needed to do was to define a data format without knowing the particular design of the experiment, and that's because that will vary across users and over time. And additionally, different experiments will call for different analysis methods. It's simply not possible for us to ship all the possible analyses that our users might want to run. And so in this case, what we need to do is to provide a standard data format that can be easily converted into whatever format the user needs to connect with their analysis tools of choice, whether that's code that they've written in the SciPy ecosystem, some existing R package, or maybe some off-the-shelf network analysis software. So what you see here is the general data format, the structure of it. What your colleague would have passed to you if they had sent you their data as well as their experiment code was a zip file containing a bunch of an experiment UUID and a bunch of CSV files. And what you should note is that each table here, each CSV table, refers to some entity that is abstract enough that it actually handles just about all the different cases that you might see in different fields. So at its heart, we're talking about nodes and vectors and passing information from one node to another at a particular time. That information may transform as it's passed, and so on. And so these are the entities that make up the data set. We also created data handling tools for the users to convert our data sets to whatever format they like best or actually need. So here is code that converts a Dallinger data set to a pandas data frame. If instead, on this third line here, instead of writing .df, if you had written .list, you'd have gotten a Python list. .json, you'd have gotten a JSON structure. Even .xls, we're using tablib, and you could have gotten an Excel spreadsheet. Under the hood, this is accomplished by making use of Odo, a data migration tool from the Blaze project, which has a network of one-to-one data conversion utility functions that are automatically chained together to convert between formats anywhere in the network. So that, for example, to convert one of the CSVs to JSON, Odo might actually convert the CSV to a pandas data frame and then a pandas data frame to JSON. And then we're also using tablib, which gives access to some additional formats like Excel, which are quite popular, at least among behavioral and social scientists in many of them. Okay. So next I'd like to move from interoperability to scalability. One of our major goals with Dallinger is to enable social science and behavioral science experiments at the scales necessary to understand emergent social phenomena. And what that means is recruiting large groups. And in particular, the real challenge for us is not just getting lots of people ever to an experiment. We can pretty reliably, if you're willing to pay for it or you design an experiment that's actually fun, it's not unheard of to get tens to hundreds of thousands of people to participate in your experiments somewhat regularly. The hard part is getting them all there at the same time. And there are some experimental paradigms that would really benefit from having a whole, basically small micro societies worth of people interacting. You can think about maybe spatial phenomena that require large groups working alone and then coming together, or things that are more like societal level phenomena. And so since we've started working on scalability in earnest, you'll see on the leftmost plot is vertical axis is the number of participants we have ever recruited simultaneously. Horizontal axis is months since we started trying. The red dots are our goal. The blue dots are reality. What you should see, oh, and just note the vertical axis is a log scale, so that nice linear rise is an exponential one. And what you'll see is that this is extremely challenging. We gave ourselves enough of a head start that there's some hope, but we're maxing out at about 250 people at once. Okay. This is an example of the second plot is just trying to max out recruitment with one particular service. That's Amazon Mechanical Turk. You basically put out an infinite impulse response of just like, give me as many people as there are. Like if you request 1 million people, there aren't 1 million people available at any one time, so you get all the ones who are there. What you can see is that we're basically maxing out in the several hundreds. The solution here is, and this is what we're working on, is to create a network of recruiters, basically a meta recruiter that says, okay, I need 800 people here in 2 hours from now. I need to look at a network of different recruitment services and figure out what's the right strategy. Okay. The next scalability problem is, 10,000 participants, okay, but then how about 10,000 bots? And you would think that that shouldn't be nearly as hard, except there's a big design decision when creating bots. I mean, I'm sure I should really talk to somebody who has experience developing like AIs for games, because they've probably hit upon this. But one of the major design decisions is at what level of abstraction are you going to define the agent? On the one hand, you could define it at a very low level of abstraction, where what you give the bot is raw pixel data from your game and ask it to make decisions. Some groups like OpenAI have actually taken that approach and had some success using modern advances in reinforcement learning, but it's very hard. It's concrete, but computationally expensive. On the other hand, what you can do is give the agent define it in a very abstract way. Say that, like in a prisoner's dilemma, don't give it pixel data of the screen, don't have it press the keyboard, just ask it, do you want to cooperate or do you want to defect? And what's nice is that it's very efficient, but it's very abstract, and you miss all of the decisions about particular behavior like reaction time and things. Those are things that are absent from such an abstract description. What we chose was actually to define our bots as a Selenium WebDriver instance that actually drives a browser pointed at the URL of the experiment server. The bot can then get input in whatever way it wants, raw pixel data, the document object model, executing JavaScript in the browser's developer console, really whatever it wants to do. And then the bot can act by pressing keys, moving the mouse, clicking around. And so the bots thus have the same access to data as human participants. This ended up being severely restrictive in terms of scalability. And so when it actually came time to needing to use this, we needed to switch to a much more abstract description. Okay. This is interesting because I'm my own moderator, but I want to be respected. Okay, good, thank you. You're my moderator now, great. Next, I'd like to turn to the challenge of reproducibility. What I'll just say quickly here is that people mean lots of different things in the behavioral and social sciences when they say reproducibility and replicability. And one way to think about this is that there's a lot of steps to doing an experiment. There's a question, there's alternative hypotheses, there's a logic and design, there's methods, there's the results, there's inferences. And what you mean by reproducibility could be something like in software engineering, a common definition of computational reproducibility would be something like, an analogy would be something like, given the data and analysis scripts, produce bitwise identical output. But then you might have direct replicability, which tries to just come to the same conclusions, analytic reproducibility, or paradigmatic. And what we've actually tried to do is to figure out what would it even look like to have a behavioral or social science experiment that has computational reproducibility. And so what we did was to create a very high-level API that where in a single function call, you can actually call that entire pipeline of running the automated experiment. And so we see here the kind of line with the cursor, data equals experiment.run. And this is a memoized function. And what that means is that you give it the ID of the experiment. And so the first time it runs that function, it goes and it actually runs it end to end. The second and later times when it runs it, however, it retrieves it from a cache so that you get bitwise identical output. This means that you can actually create a Jupyter notebook or a binder that actually has text and code that runs the experiment and defines the entire computational environment in which the experiment is run and actually achieve computational reproducibility in a behavioral experiment. We've got documentation. We're working hard on sustainability, but it's hard. We've done a reasonably good job. This is 5 years of commits, and thanks.
Oh, yeah, thanks. I was curious to hear a little more about what kind of tasks the workers, you're thinking of the workers to do, how complex they are, and what kind of quality control you might do to ensure you get spammers, for example.
Yeah, so there's two pieces to this. The first is what do we actually allow them to do, and the biggest issue is my desire is to have a stock set of tasks that anybody can make use of, but every single time anybody runs an experiment, at least in cognitive psychology, they always want to control everything about it and write their own, and so this is a challenge. Basically what I've been doing is anytime anybody creates a new task, I say, oh, can I go put this in Dallinger core so that other people can use it too? And then the question of like quality control and all that, you can basically create small tasks that are things like fill out a reCAPTCHA. At least in cognitive science, people tend to think about this a lot, and so they build into the experiments catch trials and things like that, where you can say, oh, I know that somebody really ought to be able to get this thing right because I've put the thing at full brightness, or I've made the learning problem really easy. And then you can actually, what we have is the ability to automatically give performance-based bonuses and all that, depending on automatically on the fly based on performance. Do we actually have time for more questions, or there's another? Yeah.
Your moderator ran away, but yeah, you have a couple more minutes.
Okay, I'll keep going.
How do you encrypt the data on the Amazon storage?
Yeah, so the biggest, so the biggest issue, we are almost able to do everything without storing anything that is, without storing any personally identifiable information. The only thing that's preventing that from being entirely true is that Amazon worker IDs can be linked to identities if you try hard enough. And what that means is that that's partly why we're running this on AWS, which is that at least the IDs always stay on their servers. And what that means is that like the default for Dallinger is that when you export the data, it scrubs the tables internally of the worker IDs. And a lot of experimenters don't like that because it means you can't link people across experiments at all. But it's effective in removing personally identifiable information, and that's what we want. Yeah, in the back.
How do you deal with the bias of demography of the online participants to like the validity of the research?
Yeah. So this is a nice kind of problem that's, I think, it's kind of being solved for us in that our approach is to use a network of different recruiters, and each of those individual recruiters are working hard to create useful products that allow you to recruit from diverse populations and do targeted recruitment. So just since we started this project, Amazon Mechanical Turk has done quite a lot to broaden the scope of participants that you can recruit through it. But we also have collaborations with many groups that are specifically trying to do recruitment from populations that we could never get using Amazon Mechanical Turk. For example, by doing radio advertisements in Jordan, and that one comes to mind because my name is Jordan. Like paying people via cell phone credit. So I think like our approach is like this isn't a problem I want to solve myself. Recruitment is hard. I want to have all the companies that want to do it really well do it, and then as long as they provide us with an API, we can create a kind of meta recruiter that does what we want. There's also a lot of people in. I'm going to get out of here. There's a lot of people working on this in the broader psychology community, trying to come up with ways to recruit diverse participant samples. Thanks.